Thank you, Danny. Thank you for inviting me to this workshop. I also really enjoyed the two talks of the two speakers before me. So I will not claim to know the answer to any of these questions, but I will give you some examples from our lab and then basically try to answer or share some thoughts with you based on these works. Okay, so as Danny already said, I have so far mostly spent my research on studying continuous sensory motor control. So here are two examples. The first one shows the Apollo robot grasping a Pringles container while not bumping into stuff in obstacles that are actually moving around here or being moved around by Jim Mainprice here. And I've also worked on other work where we fuse vision and touch so that the robot can do complex manipulation tasks. All right, so this is all great. But apart from sensorimotor skills, we also want to achieve long horizons tasks that require both symbolic and continuous plans. So here's an example for the Tower of Hanoi game showing two symbolic solutions with associated continuous action sequences. And these sequences consist of symbolic actions such as pick and place, transport, and so on. And the questions that I guess many speakers in this workshop have, and also the audience, is how can we plan over long horizons and adhere to motion constraints? And specifically in our work, we are interested in the case where how we can do that even if the environment is continuously changing. And the other question I particularly find interesting as well, and I'm sure many are interested in as well, is how we can scale up task and motion planning to more than just a handful of primitive actions. And to look into these questions, I'm going to present two example projects. One is by my student Toki Mikimatsu on task and motion planning in dynamic scenes, and one is by the first author is Lin Xiao, on learning manipulation concepts from instructions and human demonstrations. Okay, so let's start with Toki's project on task and motion planning in dynamic scenes, which, by the way, does not have any learning in it as of now. Okay, so what do we want to achieve here? We want to, this is an example task the robot has to solve, which I'm sure is very familiar to many of you. So basically, the robot wants to place the small box on the large box, but the problem is the box is outside of the robot's workspace. So really it has to reason about all the constraints, and the solution here is to combine symbolic and geometric reasoning to come up with, for example, one solution like this, which is grasping the hook to move the small box into the workspace and then place it onto the shelf. All right, so when you execute these kinds of tasks in the real world, there might be many things happening, right? Like, so here, for example, Toki is toying around with the robot, right? Like perturbing the objects. And the question really is like, if you have a task and motion plan, how can you adapt this to these kinds of dynamically moving environments? All right, so let's look at this. So first of all, for planning the continuous motion, we basically use trajectory optimization, where really the state is about the end effector pose in our case, and the actions are the joint torques. And then we basically solve for an optimal sequence of robot actions that minimizes basically this cost term, right? Okay, so to now combine this with a logic planner to actually find more long horizon tasks, Marc, Toussaint, and et al. Have proposed logic geometric programming and RSS 2018. So what this does is basically taking this trajectory optimization problem here and adding discrete actions, like, for example, pick and place, so denoted here by A, and then also adding some constraints that now also take discrete states and discrete actions into account. Like, for example, this F path is the continuous system dynamics, where the change depends on the discrete state S. Or here we have the term F switch, where the instantaneous system dynamics switch when the discrete action AK changes. And then, of course, we have logic, like an action skeleton that comes from logic planning. Okay, so in our work, we're going to adapt that kind of framework. And for that, we first, of course, need this logic planner and the predicates. So we basically use strips planning, and here's the planning domain for this. So we have a bunch of propositions for this example with the pick and place of the cubes, and a bunch of actions with preconditions and postconditions, a set of objects like the table, a ball, and so on, and an initial state and a goal state. So using this kind of domain, we can now basically search for solutions. There are often multiple ones, and this is an example of how such a planning tree may look like, okay? So essentially, just basically using basic search algorithms, we can find a valid symbolic plan for this. Okay, so now this symbolic plan has to be checked on whether it's feasible, right, for the robot. And for that, again, we come back to trajectory optimization. And here's the solution lined out that Marc, Toussaint et al. From RSS 2018 have proposed, where they basically use logic geometric programming plus motion optimization over an augmented joint state. So that's a really nice formulation. So the sum of these trajectory across all time steps results in a banded Hessian that can be inverted efficiently. And the constraint functions, though, they depend on the entire trajectory, as you can see here. And the coupling over the entire trajectory actually makes the Jacobian of the constraint function quite complex. And another disadvantage is that if you optimize over a joint trajectory, this trajectory becomes invalid as soon as the environment changes. This is something that we wanted to improve on. So what we what we done is we reformulated this problem by not optimizing anymore over joint space, but actually optimizing over relative Cartesian frames. And so this now becomes an object-centric problem, and it has several advantages. So let's look at the examples to explain this. So here, the robot may want to pick up this green box and place it on the blue shelves, right? So these are like two primitive actions, pick and place. So for the first pick action, you would first control the end effector relative to the target block to align it with some Cartesian frame. Now there are many ways to actually grasp this green box. So it can have many different relative positions within this end effector. And the problem if you pick a joint space formulation is that basically the way the green box is placed within the end effector influences how you will need to control the arm for placing this box on the blue box. So if you would optimize over joint trajectory, this needs to be adapted. However, if you use an object-centric representation, we basically just need to know where this box is relative to this blue box and then control it in that way, right? So this is really the overall idea. And the contribution of this work is essentially to take this nice logic geometric geometric programming and formulate it to actually optimize over relative Cartesian frames. And so we basically keep this logic planner, and now we optimize over these size. And what is happening now is that this nicely decouples the constraints over time. So it becomes much easier to formulate the constraints. Just the objective becomes more complex. But what is nice now is that the plan stays valid even if the objects are moving around in the scene. And we can use a low-level operational space controller to deal with the whole jorts, right? All right, so now here's how the system actually looks like. So in the planning stage, we basically use our symbolic planner to find logic plans. Then we use the optimizer to actually check which of these logic plans are actually feasible for the robot. And we find an optimal frame skeleton that we then execute in the execution phase here, where we basically use this reactive controller, basically an operational space controller, to execute this plan. And this really runs at a kilohertz. One interesting thing is that I think it's something that needs to be added is we have not yet added a way to actually trigger replanning on the level of the frames or on the level of the symbolic plan while the environment changes. So that's something very interesting to look at in the future. But now let's look at what the system can do. You have already seen this video where we basically found like 2 valid symbolic plans, and these are basically the continuous motions using these object-centric representation. Okay, so, and as I've also shown you already before, this plan that is based on an object-centric representation now stays valid, even if the objects are moving. So we don't need to replan the relative Cartesian frames, and we don't need to replan the symbolic plan. This just stays the same. Okay, so of course we also want to make that work in the real world. So here we have like a demonstration of this where we have a robot arm basically executing the symbolic plan. And we use visual tracking by combining depth and marker observations here. And here you see Toki's arm, basically, again, like annoying the robot by perturbing the environment, perturbing the robot. And you can also see that the robot can still execute this plan in real time. So you don't see like a ×10 here, for example, in this video. So this is really happening online. And the reason why it can do that is because we don't do any expensive replanning here. All right, so just to summarize this part of the work, the main idea here was that we basically use symbolic planning to create this action skeleton that translates into a constrained motion optimization problem. And the algorithmic contribution here was that we reformulated the trajectory optimization problem from joint space to actually optimize over relative Cartesian frames. And the result is the task and motion planning framework that really works in dynamic environments. All right, so so this was the first part of the work I wanted to present, and I also want to present a second work that aims at scaling up this first framework. One disadvantage of the first framework is, and maybe of many task and motion planning works, is that you really have to define this planning domain by hand, right? So it's very annoying actually to define these actions, and specifically to define them such that they translate into constraints of an optimization problem. So it's very tedious, and if you want to scale this up to potentially many different verbs and actions and derive the action conditions and constraints automatically, this is really not feasible. So we really wanted to know how we can scale this up. And so here in this second project that I want to present is basically a work where we endow a robot with the ability to acquire manipulation concepts. And these manipulation concepts can be seen as mental representations of verbs in a natural language sentence, like the one shown up here. And given an initial scene image, when we send various instructions that like put something behind something, we want the robot to generate motion trajectories that accomplish these tasks. Okay, so what's the general idea? To achieve this goal, we construct an embedding space that associates task instructions and scene images with these motion trajectories. And by constructing an embedding space of manipulation concepts, we gain several benefits. First, we can specify the manipulation task with language instruction instead of goal images. And describing the task with language is much simpler than providing a goal image. And second, we obtain a multitask policy to represent diverse manipulation skills such as open something or close something. And third, by training a diverse set of manipulation tasks, our policy can generalize to even novel, similar instructions. So how do we train the robot to output trajectories to accomplish these tasks? So in our approach, we basically use learning from visual video demonstrations of people. And this allows us to avoid reward engineering or kinesthetic teaching or teleoperation, which are all time-consuming and difficult to scale up to a large number of tasks. And for the video demonstrations, we used the 20 billion something-something datasets. It contains around 200K video clips with 174 different action classes. Each video clip is annotated with task descriptions, such as putting something on a surface or moving something up. And one thing that is a problem here is that there is a large domain gap between the human demonstrations and the robot simulation. So here, for example, on the left, you have close something as an example, and you see 4 examples, but they're really different from, for example, this robot demonstration. And so what we really need if we want to do this is a visual demonstration method that can handle different backgrounds, different viewpoints, different objects, and so on, to actually overcome this domain gap. Okay, so what is our main idea here? The main idea is to use an action classifier. We use an action classifier that is trained on these human demonstrations to score the robot simulation. So this action classifier is trained on the 20 billion something-something data set and then scores the robot video. And the score represents how confident the video classifier estimates the robot video to belong to the corresponding action label. And then we run reinforcement learning to update the motion of the robot, where the reward is the score from the video classifier. So why do we think that works? This action classifier really takes the entire video into account, and it has to really generalize over all these different appearances. And what our hypothesis is that this action classifier has to capture motion instead of appearance. And this motion for close something might be very similar in this robot simulator, although the appearance is very different. Okay, so how does this exactly look like? Here's our architecture, where we first send a language instruction and an initial scene image as input to our model. And this is then concatenated by concatenating the features to provide semantic context here. And then we have in the middle a policy generation network that outputs a motion trajectory, which is specified actually as a dynamical system, and the network has to output a goalpost and a series of forces to perturb the otherwise straight line trajectory. So next we execute this entire motion trajectory with the robot in simulation and render to get a video. And this video is sent to the action classifier to get a score, which is used as a reward. And then we run reinforcement learning to update the parameters of the motion trajectory to maximize the reward. All right, so we actually test this on 78 different tasks in simulation that match up with this 20 billion something-something data set. And for each of these tasks, we train a policy using this pipeline that I just showed you. And here are some examples of these policies for one particular instruction. So this is close something. So note that the difference here is that the policy has to work with the same object, but in different poses. Here's another example for tilt something with something on it so that it falls. It's like the opposite of what Wei Wei wanted in his talk, actually. And so now what we have is we have 78 single task expert trained in this way, each of which outputs motion trajectories to accomplish a desired task. But what we wanted in the beginning is a multitask learning framework where we have like one policy that basically can take in these instructions and output the correct motion. And the way we do that is we train this multitask policy by running behavior cloning on the previously learned single task expert trajectory. And the result is a unified model that can take in various task instructions and scene images as input and output trajectories for 78 different tasks. So here are examples from this one multitask policy for 78 different tasks. And you see they're very diverse and very funny and they actually, some of them work better than others, actually. And one interesting effect of this model is that we can generalize to novel task or natural language instructions that are similar to the ones we trained on. Okay, so just to summarize this paper, which is, by the way, an RSS paper, and if you want to talk to the first authors, please go to their session. It's paper number 82. And the main idea is here that we learn an embedding space for manipulation concepts indexed by natural language instructions. And the algorithmic contribution is an imitation learning framework from human video demonstration that uses an activity classifier to provide the reward, rather than doing, for example, visual scene dynamics to reach a goal image. And the result is a multitask policy that can execute 78 different tasks indexed by natural language instructions. So these were the two example projects, where the second one was really thought to provide an automatic way to learn primitive actions for the first one. But we're yet working on bridging these two. So I want to come back to my title slide to close this talk. I'm almost done. So my questions that I posed in this talk was like, if, what, and how to learn in task and motion planning, which I don't know is grammatically correct, but just stick with me. So I think, yes, learning is useful in task and motion planning to scale up these symbols and to generalize over different appearances. I'm not so sure about what to learn, actually. So in this work, we didn't use any learning that I presented, but I think we should learn the low-level primitives. We've also have other work where we do not planning, where we also have the task planning done actually by a topological planner. It's a soft problem, no learning is needed, but we need to learn the low-level, the complex low-level action here of actually nodding. But then we have also other work where the low-level actions for in-end manipulation can be implemented by well-known torque controllers, but the high-level policy is actually hard, and therefore we learn it. So saying like, I'm not quite sure what to learn in motion planning. There are many different things. And to me, it seems that it really depends on the task, what you want to do. And what worries me a little bit is that basically what you learn is completely task dependent. And also it depends on what we have already figured out on how to do analytically, right? So I don't really know what is the best to learn. Right, so how to learn? Well, we've many different nice methods. We used often reinforcement learning methods or variants of imitation learning. We use model-based and model-free. There are so many great models and each have their pros and cons, so I don't have a definite answer. And with that, I want to thank you for your attention. And I would like to thank my amazing students who are doing all the work and all my funding sources. Thank you very much.